I want to thank Professor Judea Pearl because he changed my life, because he changed the way I think about anything. He has a book on causality, he has another book on the book of why, which are very important. And this book is really essential for future of causal machine learning, I think. So we have a paradox, removing paradox by choosing the proper language. For example, my neighbor's roof gets wet whenever mine does. If I hose my roof, it will get wet. But we can adjust the language by saying my neighbor's roof gets wet whenever mine does, except when it is covered with plastic or when my roof is hosed. We have Forex example as well. If Aussie dollar USD is more than a threshold, pound USD, Euro USD regression error, we call it the spread, gets bigger. If Aussie dollar USD is more than a threshold, spread is reduced. So we just adjust our sentence and we just adjust our language and we say if Aussie dollar USD is more than a threshold, pound USD, Euro USD regression error gets bigger except when Aussie dollar USD is higher than U. So we have some confounding variables. We call it K because it has both. It has a direct effect on both dependent and independent variable. It has a direct effect on both treatment and outcome. So, for example, K is Aussie dollar USD. It has a confounding variable. It has a direct effect on both USD CAD and the spread. So conditional independence is very important. For example, using this definition, it's quite obvious that using the knowledge of Z, it is enough to identify X, to understand X. We don't need Y anymore. And there are some relationship between these. And for example, we have a Bayesian networks. We have a season, rain, wet, slippery, and sprinkler. And uh, uh, separation is a concept that allows us to make equivalence relationship between different causal structures. In fact, you can find equivalence classes up to the separation. Here, for example, we say x and y are d-separated given z2. It means that the knowledge of z2, so it is just it's enough to understand it, to identify x. We don't need any other variable. So in this example, we say that x2 and x3 are d-separated by x1 because both paths are blocked by z. And we have a probabilistic implication of this separation. So if we just say that we want to do some intervention on x3 variable on a sprinkler, we break the lines that is connected to that because x3 is now it's just fixed. If we want to know the effect of x3, that intervention, on the outcome. So we have a new distribution. So we had a distribution, we had a joint distribution just before doing that, and we have a new distribution just after doing intervention. And in the next lecture, I will show you how easily they're related by fraction. So we have a nominator and denominator. They're easily related to each other. That is, I mean, the distribution before the intervention and the distribution after intervention are easily related to each other, which we can understand. We can have a basic idea of what is going on. And here we have functional causal model. And so in my previous lecture, I talked about potential outcome model, the framework pioneered by Fisher and Neyman. And but the current infrastructure, the current framework that I'm talking about, which is for Judea Pearl, it is much more elegant, much more interesting because he's talking about integrated counterfactual approach. He had a tool in potential outcomes. It's just a methodology. It's just a technique. But in a counterfactual approach, as epistemology, like in philosophy, is really show you how to do that. So in counterfactual approach, your interpretation is expect inconsistency and causal effect of the past, but interpretation in potential outcome framework is a potential outcome of the future. And as I said, it has roots on Cox Fisher, but the new approach has uh, is is done by people like Campbell, Cook, and of course Judea Pearl. A great example of counterfactual is could be we can now calculate the probability that a subject who died under the treatment would have recovered had he or she not been treated. He's died, so how could we do that? But we can do it with counterfactual because now we understand what is the effect of other variables. For example, some we have some other variables, and we can calculate the effect, we can measure it. And as I say here, we have abduction, we have the evidence, we want to find the probability of you, for example, the noise, any other variables, covariates, for example. Covariates could be some such a variable. Some variables that are not but we don't know nothing. We know nothing about it. So in action, we replace it with X. So we do X. We do the intervention, and the final step is just prediction. We use the modified model to compute the probability of Y. So as you see evidence, for example, in the last example, X and Y, X is treatment, Y is if it is died or recovered. And here we have the evidence. We find U. U is the noise because there are some other variables, maybe age, maybe sex or other variables could have had any effect on that. So this is the algorithm, and